Hello, everyone. My name is Mikko Mäkelä, and I work as a research professor of intelligent biomass processing at VTT, Technical Research Center of Finland. And now I'm going to give you a quick overview of digital textile identification. I'll give you a little bit of the background and then some principles on near-infrared spectroscopy, and then something on the possibilities and potential future challenges within digital textile identification. Okay, so let's start with a market approach. So the textile market is currently booming. We've seen and we are going to see annual growth rates of around 10% even within the next few years. And the production of textile fibers and the number of sold textile items has doubled since the year 2000. And we also know that these increasing production and sales quantities, they're also related to decreasing product lifetimes. And what this means in practice is that we're basically buying more clothes and producing more clothes, but we are using them less. And there's only one way this is going to go, is that we're going to see an increase in textile waste. The statistics on textile waste are a little bit hard to get updated ones, but from 2012, at least in Finland, the estimate said that consumer waste textiles from domestic households were around 70 kilotons a year, and that's approximately 13 kilos per person. If we look at a little bit of the produced fibers, we see that polyester is the largest fiber fraction, then followed by cotton, which is approximately 1/4 of all produced fibers. And then we get the cellulose fibers, where you see viscose, modal, lyocell, and so forth. And in addition to this, so the increasing trends on textiles and decreasing textile lifetimes, we see that we're going to get international EU regulation on which says that member states have to start collecting textile waste by 2025. And in Finland, the government has even stated that we're searching for alternatives to start this even sooner. So we see that we have now an imminent need for ways to digitally identify and then even sort textiles. And then a couple of words on digital textile identification. So basically this would enable a shift to automated identification and textile sorting. There are ways to do this, and most of the systems are now based on near-infrared spectroscopy. And in near-infrared, we gather a spectrum which basically works as a bit of a chemical fingerprint. As you can see on the image here on the right, we actually measure sample reflectance in respect to a reflectance of a standard. And then once we've calculated reflectance, we can then convert this into absorbance, which then, according to the Beer-Lambert law, which states that everything else being equal is then directly related to the concentration of the absorbing component. What you can say about NII is that in principle, it's relatively quick and easy to measure, but complicated to interpret. And you see this image of the spectrum there on the right. The peaks of the spectra aren't really super well resolved. So if you compare it with mid-IR, you'd see sharper, easy to recognize peaks, which means that we then have to use applied mathematics and generally chemometrics for interpreting the spectra. And we have different kinds of systems for measuring a spectrum. And the sort of lack of transparency regarding the measure and especially normally the mathematics makes the comparison between the different methods slightly challenging. One thing that can be said is that if we measure spectra from an arbitrary point within a sample using traditional spectrometers, we generally require pre-sorting. And I have a couple of examples for you on that on the next slide. And here we have some examples on different systems for measuring spectra and digitally identifying textiles. These examples are from the Finnish context, but the principles apply also to the majority of other systems. And here on the upper left, you see equipment that is situated in Lahti Applied Science School, where you basically have a conveyor belt where you put the textiles, and then you have a spectrometer which stays in the same place that then measures the spectrum from the textile moving under the instrument. And then you have pressurized air, which then directs the textiles into the different sorting lots. And here in the middle, you have an example of a miniaturized NIR sensor. This is a Finnish company, VTT spin-off. And it's obvious that the sort of the technical qualities of all of these sensors aren't really comparable, but the novelty of these miniaturized sensors is that in the future you might be able to couple this to your laptop or your phone, measure the signal, then send the measurement results to the cloud, where you would have some prediction or calibration model that would then predict textile characteristics and then return the result back to you. And obviously you would be very competitive in terms of price with this solution. And then lower on the right, you see an image of a hyperspectral camera that we are currently using at VTT. And the specialty with hyperspectral cameras is that you're not only measuring one average spectrum from an arbitrary point of the sample, you're actually gathering a hyperspectral image where you have a spectrum in each pixel. So the camera is steady in the same position, and then you have a sample moving under the camera, and you construct the image. And then this then gives you entirely different kinds of possibilities to identify objects, and then also to evaluate the chemical composition and the variation in the chemical composition within the textile material. And then a couple of general words on hyperspectral imaging, and I often use this example when we compare it with visible and digital imaging. So if you take an image with your digital camera, you're generally measuring 3 different wavelengths within the visible range. So this would be red, green, and blue. And what a hyperspectral camera does is that it records hundreds of different images continuously. And normally, at least the majority of these wavelengths are situated outside the visible range. You have a figure here on the right where you see some of the principles of the imaging procedure. So this is a line scanning camera as well, where the sample would move under the camera. You would gather a 3-dimensional hyperspectral image data set, which would then contain very many different images. And then you would use applied mathematics to interpret this image. And using the information in the image, you could then, as an example, do some kind of classification procedure where you try to identify different materials from each other. The benefit of hyperspectral imaging is that you then combine the chemical information provided by the spectrum in each pixel with the spatial information of a traditional image. And it's suitable for organic and then also for some inorganic materials. So you could, as an example, use it for trying to identify or separate different kinds of rocks or minerals, and then also a wide variety of different organic materials. The background is in remote sensing and satellite imaging from the 1970s. And from there on, it has spread to a wide variety of different applications. So you see the defense industry, mineralogy, food and agriculture, medical diagnostics, the pharmaceutical industry, recycling, etc. And here you see a concrete example on hyperspectral imaging and using it to evaluate the chemical composition of a textile. And here on the left, you have a digital image taken in the visible range of a textile that we had special made at Aalto University here in Finland. And what you can see from the visible image is that you see that there's a shape inside the textile sample. You can see the outlines of the shape, but you can't really make distinctions whether it's made of the same fiber or not, because you're only looking at the color, and they both are white. So you can't make a distinction in that. When you take a hyperspectral image of this sample and then you do image exploration, you see an example here in the middle. And this image basically gives you an idea of the chemical contrast within the sample, so chemical differences between different areas. And from this image, you would then get an idea that very likely the heart shape and the surrounding fabric, they are somehow chemically different. And then when you would interpret the changes in the spectrum based on this chemical contrast image, so you'd go one more to the right, you'd get an idea that the warm positive colors in the image in the middle would correspond probably to polyester, and the negative cold colors, so the blue in the image in the middle would then correspond with cellulose. And this would give you then an idea that the surrounding fabric is likely composed of cotton or some other cellulose fiber, and then the heart shape in the middle is most likely polyester. Now, if you would want to even more certain results, you could then say run a classification algorithm on this image, or you could create a calibration model which would then predict, say, the polyester concentrations of the individual image pixels. So this gives you an idea of the power of hyperspectral images in analyzing textile materials. And we at VTT, we do a lot of imaging and textile research. We've been involved in some national projects here in Finland, including the Telaketju 1 and 2 projects. And Telaketju 2 actually included some piloting on using hyperspectral cameras and robotic sorting systems for textile identification. And the idea there is very similar to the cartoon that you see here in the right. So you have some kind of a conveyor belt where you have textile materials moving. You have a sensor or maybe multiple sensors that take images or gather some kind of other information on the textile samples. And this sensor information you would then interpret using chemometrics or machine learning or some kind of an AI engine that would then guide a sorting robot to sort the materials in right places. And the results from this piloting activity, they were very promising. So I've listed some examples here where you see that sort of roughly classifying different textile materials into different fiber types: cotton, polyester, polyamide, viscose. The results were very encouraging for textile identification and robotic textile sorting. And we are now also continuing the work on hyperspectral imaging of textiles. We're currently at VTT, we're part of this Phoenix project, a national project here in Finland, funded by Strategic Research Council of the Academy of Finland, sort of directed towards revolutionizing the textile production and consumption systems into a more sustainable direction. In this Phoenix project, we do part of the work that we do is directed towards developing future machine vision for textile recycling, and there we do textile imaging from the perspective of a chemical recycling. And a couple of the things that we've done already is that we've focused on separating different cellulose and polyester fiber mixtures and predicting the chemical composition of these fiber mixtures. And you see an example here on the right on some of the images that we predicted. So in this image, you basically have two rows of samples. In the upper row, you have a cellulose and polyester fiber blend. And then in the row below, you have a pure polyester sample. And in this image, in the first column, you have the digital images of the textile samples. And you see that there's differences in terms of sample color. And there in the column on the right, you have the predicted polyester concentrations of these samples. So from these predicted images, we can then see that the the red areas in the sample, they correspond with cellulose, and then the dark, almost blackish areas, they then correspond to a higher concentration of polyester. And then in the lower row, you see that even if we have visible differences in the textile sample, we don't see these differences in the predicted image because we are purely predicting chemical composition and the sample is entirely composed of polyester. We also do identification and classification of different sort of cellulose-based fibers based on chemical fiber structure. You see an image here, and this also, like before, sort of corresponds with the chemical contrast between different sample types. This work is still ongoing, so I'm not going to go into details here, but the idea is to sort of separate fibers based on chemical fiber and sort of molecular structure. And the results seem promising, and I have very high hopes for this work. What is key in this slide is actually the concept of detailed chemical information. And one of the things that I want to argue that in the future, when textile collection, sorting, and recycling improves, we're also going to see an increase in all of these new and exciting ways to recycle and even regenerate textile fibers. And this means that we'll be able to produce recycled fibers which can have properties that are even better than possibly the virgin alternatives. And this means that we're also going to need an entirely different level of detail also in terms of digital textile identification, which is something that we should definitely keep in mind when we develop these materials for future textile identification. Okay, so a couple of things to conclude here. So increasing consumption is coupled with decreasing textile product lifetimes, and we also see this EU-wide regulation that then necessitates that we have to start separately collecting textile materials, and we also have then a pressing need to develop these digital textile identification systems to optimize also the sorting of textiles. And most of the systems that we currently have available, they're based on near-infrared spectroscopy, which is generally relatively quick and easy to measure, but then complicated to interpret. And if we use traditional spectrometers, which then measure an average spectrum from some arbitrary point within the sample, we're still going to require some sort of pre-sorting of the textile materials. If we then go towards the hyperspectral imaging side, we get the advantage that we're going to be able to identify also objects and then even evaluate the chemical composition and variation in the composition within the textile material. And the take-home message here is what is the type of information that we're actually going to need for future textile recycling. And with that, I would like to conclude and just quickly mention here that at VTT we strive to go beyond the obvious. And if you have any questions or ideas or others, feel free to contact me through Twitter or email, and you know the drill. And with this, I would like to wish you all the best for the year 2021. Thank you very much.